Single-phase transformers, part 3 of 5. What we're going to be looking at in this presentation is transformer tests. What are some bench tests or field tests that are done on transformers to validate some of the readings? We're going to look at some further transformer calculations. We'll look at the effects of loading on transformers and a deeper discussion on how a transformer functions. And we'll finish with transformer taps and the reason for them. Transformer tests. Transformer tests typically are two different categories: open circuit test and short circuit test. Let's see what the difference is between them and what they're going to tell us. Open circuit tests are used to determine the total core losses of the transformer. Core losses are caused by hysteresis and eddy currents, and overall, the magnetic flux density in a transformer will remain almost unchanged from full load to no load. And really, the magnetic flux in a transformer's core is what is going to determine the core losses. So the reason for an open circuit test would be to determine what are the losses just of the magnetic components within the transformer. So remember, watts are equal to volts times amps, and we're not using any sort of phase shift here, so no power factor. So there's two different ways to do an open circuit transformer test. You need the rated primary supply voltage or rated secondary voltage. Doesn't really matter, it's kind of either or. In this particular situation, they are energizing the secondary with a rated secondary voltage, and they are putting a watt meter in place, and the watt meter simply measures the watts of power loss, or the watts of power that are being consumed in order just to magnetize the core. The alternative would be to place an ammeter and a voltmeter and to take those two values and multiply them together, giving you total core losses. The very small amount of current that you're going to see flowing through the primary is called the exciting current, and that exciting current is the value of current required to magnetize the core. And in magnetizing the core, the only power that's being used is for that purpose, and then by measuring it, we can determine the total core losses. A short circuit transformer test can be used to determine the copper losses of the transformer when the transformer is fully loaded. This is the I²R losses caused by the current flowing through the winding conductors of the transformer. And in doing this test, it's easier than loading the transformer secondary with the actual full load, because that could be hundreds of amps. And there are applications of load testing, but this is not what this test is for. It's to determine what the total amount of full load loss would be in the transformer. So there's two different ways to do this. The first way is to put a watt meter into the circuit, and the watt meter looks like we need to have a wire connected in there. Hold on. There we go. We've got a wire connecting our watt meter in, so it's got current flowing through and a voltage potential, and it is a variable AC source. And the process is that we slowly increase the primary voltage until the rated primary current is achieved. So you would be slowly increasing this, and notice I have a jumper. I have a dead short across the secondary, so you're very slowly increasing this until your meter registers what the rated primary current is, and at that point you stop increasing the voltage, and then you record the voltage and current, or you just read the watt meter, one of the two, and it would tell you the total fully loaded copper losses of that transformer. So it's an interesting application. It's very simple to do, but it requires a variable AC source, and you are intentionally short-circuiting the secondary of the transformer. So in doing those two tests, you could work out the total losses of the transformer, and we know that with our percent efficiency formula that the P out divided by the P in requires us to know what the output and the losses are, and the losses are made up of copper and core losses. There's another short circuit test that we use sometimes, and that's called the percent IZ test. So the percent IZ is the percent current impedance, or a value of impedance that's required, the voltage required to overcome the internal impedance of the transformer to generate the rated current on the secondary winding, which is really quite a mouthful. And I would really say it's not of significant value for you to understand fully what all of the different implications are of this particular measurement. What it's used for an electrician is to calculate the maximum secondary fault current a transformer could deliver in a short circuit condition, and that is important. So the way that we would actually do the test is the same as the previous. We have a variable AC source, we have an ammeter and a voltmeter. And this time, instead of taking the two values of amps and volts and multiplying them together, what we're going to do is slowly increase that AC source until rated current is read in the ammeter. And then we're going to take the voltmeter, we're going to measure or record that measured voltage. So the measured voltage divided by the primary rated voltage of that particular transformer times 100 would give us the transformer's percent IZ. Now this will typically be on the transformer nameplate, but importantly, its use. What do we use it for? Well, we use it to calculate how many amps will be flowing in the secondary if there is what's called a bolted fault. If there is a bolted short circuit fault, that's the absolute worst case scenario possible. How many amps is this transformer capable of pushing? Now we all know the short circuits are a lot of current, but exactly how much current? How much current will be flowing in there when there's a dead short? So we use the percent IZ in order to calculate this value. A transformer's secondary short circuit current is going to be equal to the rated full load current divided by the percent IZ, and the percent IZ is a decimal, so you're removing it from percent and you're moving the decimal 2 places. So the first thing we would need to know for this transformer is what the rated secondary current was. And the rated secondary current would be our 100 kVA divided by 240. Gives us 416 and change amps. We would then divide that by 0.035 because our percent IZ is 3.5. We divide those two values and we end up with an absolute maximum value of fault current of almost 12,000 amps. This is important because any switchgear or equipment that we place into the secondary circuit needs to have an interruption rating. And the interruption rating needs to be able to handle that current without failing. So any equipment connected to the transformer secondary must have an interruption rating that is larger than the fault current calculated. So we calculated almost 12,000 amps. That means that based on the ratings that are available from manufacturers, I'm probably going to be using fuses and a disconnect that have a capable interruption rating of 15,000 amps. They come in standard values. They're certainly not categories you need to memorize. That's simply what we would probably have available to us. Let's talk about the effects of loading on transformers and have a deeper discussion on how a transformer actually functions. So remember from a previous presentation, we said the primary and secondary are linked or coupled together through magnetic flux. Magnetic flux is what is going to couple these two together, and that load current magnitude will cause an effect in the primary current's magnitude. So if it increases, it caused the primary to increase also. And if it lowered, it caused also a reduction in the primary current. Now, why? How is this going to take place? And so we need to have a general understanding of how magnetic flux and counter EMF is actually occurring and what happens inside an individual winding. So let's start with this. This is a typical coil of wire, and there is going to be a source current that flows through this coil of wire, and we're going to look at a split second in time as the current value is increasing, and as the magnetic flux increases, it is going to break across a second winding in the coil. So this is looking at just basic self-induction on a coil of wire. So it will increase, and what it will cause is a voltage to be induced into the next turn of the winding, and that's called an induced or counter EMF. Now, EMF will cause current to flow, which would then obviously make lines of flux, concentric circles surrounding that winding. Now, what's going to happen? The currents are traveling in opposite directions. Obviously, the source current is larger, but the induced counter EMF will cause a reduction, essentially slow it down. So it will reduce that primary current or slow it. So let's take a look at that again in the animation. Eventually, it will get rid of that counter EMF. So counter EMF reduces source current. So here's our source current, EMF expanding, cutting lines of flux on that secondary coil. That causes lines of flux to be set up in opposition to the original primary, and that means it's going to slow the main source current or reduce its value. So why is this significant? Well, it's significant because counter EMF, when it increases or gets larger, so when this counter EMF gets larger, there's more lines of flux and the currents that is set up there is in the opposite direction is larger, it reduces the source current. So source current decreases. In a transformer, there's more than one winding. So I've just shown the primary winding. In a transformer, there is a secondary winding, and the secondary winding flux will oppose and reduce the counter EMF, the blue that we see here. So the secondary winding will also generate its own magnetic flux. And what it will do is it will oppose this flux here. And remember, what does oppose mean? Oppose means reduce. So if the secondary flux, that's my yellow, opposes and reduces the primary counter EMF, what will that do? If it lowers the blue, if it makes it smaller, that means it's less opposition to this main current that's flowing through the primary, and the primary current will increase. So let's take a look in a few different slides how this concept will manifest itself. So when I first energize a transformer with no load on the secondary, the transformer's primary will draw a small current from the source known as the exciting current. And that exciting current is simply magnetizing the core, and there is magnetic lines of flux, and there is a counter EMF that is generated on each of these individual windings. I'm simply only showing one here just to make it a little bit clearer because there's a lot going on. As soon as we put a load on the secondary, because there is current flowing through this winding, that means that it is going to generate its own secondary flux. So this secondary flux is going to start traveling in the core as well. But remember what we said, the secondary flux is going to oppose the counter EMF. And if it opposes the counter EMF of the primary, think of it as restricting the primary current. So what's going to happen? If it lowers this, if it lowers the primary counter EMF flux, makes it smaller, that means that the main source current will rise in value. So it will get larger. And essentially what it's doing is it is attempting to equalize the primary to the secondary. So as soon as more current flows in here, there is going to be more cutting of lines of flux, and that will again increase the counter EMF on the primary winding. And in doing that, what it will do is equalize the flux density between the primary winding and the secondary winding. As in, there will be no more primary flux than there is secondary flux. And that means that overall, as the transformer is fully loaded or partially loaded or very little loading, the overall net magnetic flux will be pretty much equal, as in there's very little difference. What we've just looked at here is split second in time as the primary reacts to the secondary. The magnitude and the type of load supplied by a transformer will have an effect on its secondary terminal voltage also. Now, there is a significant amount of phasor diagrams that we can use to help illustrate this in different ways. What I found in the past is that most people find it easier simply to remember a few standards of what we can anticipate in the real world. So the first thing is that when a transformer is connected with no load on the secondary, it will have a secondary voltage that is higher than its nameplate rating. This is the same for almost any type of source out in the electrical industry. You would anticipate a higher voltage, and the reason for that is that with no current flowing through the secondary, there is no voltage drop on all of the resistance inside that winding. And that voltage drop, and also to do with reactance, magnetically between the primary and secondary, you do not get a reduction in value. So if you are commissioning and you're testing the transformer to see if it is connected properly and everything else, well, you would anticipate having a higher voltage than what the nameplate value states. At full load, you should see a voltage across the secondary equivalent to what the secondary voltage rating is, so 240 volts. So I'm supplying a 100 kVA load. It's a 100 kVA transformer. I should be reading 240 volts AC. If I were to exceed the rating of the transformer, which is not advisable, but if I were to exceed it, and now I'm driving a 150 kVA load from a 100 kVA transformer, I would anticipate the voltage at the terminals of the transformer to start dropping. So they're going to be lower than the nameplate rating. Not only does load affect secondary voltage, and the load obviously is going to affect it due to line drop in the windings, inductive reactance, and magnetic flux reactions, but also the type of load. So this concept here, and it's also reflected in alternators when we're supplying loads off alternators, inductive loads will cause the secondary terminal voltage of a transformer to drop further than an equal amperage value of a resistive load or unity power factor load. As in, the same value of current inductive load will cause the secondary voltage to drop much quicker than just a standard resistive load. Capacitive loads can have the effect of increasing the secondary terminal voltage, and it can actually increase it to a value that's higher than the nameplate rating. So interesting to consider, and there is lots of data to back this up. However, a full extrapolation of the calculations and the phasors involved, I find, does not lend itself to doesn't make for good use of time when considering other applications we need to explore further versus this one small concept. So a transformer's ability to maintain its secondary terminal voltage at the nameplate voltage rating is referred to as its percent voltage regulation. And so that is a calculation that is done by taking the voltage at no load, which is going to be quite high, subtracting the full load voltage, and then taking the product of that and dividing it by full load times 100. That will give me the percent voltage regulation. It's desirable to have a transformer with a very small percent voltage regulation, where it's telling me it will only deviate maybe 1 or 2%. A transformer with 15% voltage regulation would be considered very poor in its engineering and design. Let's talk about transformer taps. Transformer taps come in two different varieties. There's secondary taps and primary taps. So what exactly is a tap? Well, a tap is a connection to the winding without making a separate winding. So on the secondary, if we had secondary transformer taps, they would be used to provide multiple different secondary load voltages. So sometimes you see these on smaller VA control transformers where, depending on which connections you use, you can elicit different voltages. Primary taps are used in a different way. They're used to ensure the volts per turn rate is maintained when the incoming primary voltage is lower or higher than the transformer's rating. The incoming primary voltage could be low due to the transformer being a long distance from the supply source, which would be the case on single line high voltage distribution where we have pole mount transformers out to an acreage or something. So the implications or the desirability of primary taps are best illustrated with an example. So here is two transformers. They're both 1200 volt primary, 240 volt secondary, 1200 volt primary, 240 volt secondary. Both of them have a low incoming voltage, 1000 volts instead of 1200. This transformer over here has taps, and we'll see what exactly those are doing. But first, let's just see what the result is. So with the transformer on the left, 1000 volts coming in means that I'm not going to get my rated secondary voltage. And that's because the volts per turn has now been reduced, hasn't it? Instead of getting, depending on how many turns there are, let's say it's 100 turns. If we had 100 turns with 1200 volts, I would get 12 volts per turn. But now when I only have 1000 volts, I would be getting 10 volts per turn. And that means that the voltage produced on the secondary is low, as you'd expect. And this is not desirable. So if I have a tap available to me on the primary for this low incoming voltage, it ensures that the voltage generated or induced into the secondary remains at its rated value of 240. So the purpose of using primary taps is to ensure that the secondary voltage remains the same. So here's an example of some typical primary tap ratings. They're usually in percents, and they might say 95, 105, 110%, or they might just say plus or minus 2.55 and 0%. So this is telling us the actual primary voltage, right? We can see here this transformer is rated for 4160, 240 volts, 500 kVA. It's telling me if your voltage is this value, connect your circuit conductors to the negative 5% tap. So you'd connect here and the negative 5. And in doing that, you'd be decreasing the number of turns connected in the primary winding, right? Look at where it physically is located. There is less turns here than there is from the plus 5 to the common terminal. 0% would be 4160, and then 4368 would be plus 5. That's all the way over here. And so it's adding or increasing the number of turns connected in the primary winding. So the whole purpose of this is to ensure that the volts per turn remains the same, even if the supply voltage is not equal to the transformer rated primary value. Here's another example, this time using the ratios, voltage ratios. So now what we're looking at is a tap percent. So 95, 97.5, 102, and 105. So now what we have is 9.5 to 1, 9.75 to 1, 10.25 to 1, and 10.5 to 1. So the ratio changes slightly, and it changes so that we can ensure that we continue to have 240 volts on the secondary. So here's some examples of this application. Here's a three-phase transformer, and you can see that it has taps and voltage. So 480 volts is what this transformer, well, 460, I suppose it shows here, 460 volts, and it's going from 460 to 460Y. So it's a specific type of transformer for an application that we're not going to cover right now. But you'll notice that there's 3 different taps, and it says jumper connection. There's tap 1, 2, 3. 1, 2, 3, 1, 2, 3, and there's 3 sets of them because it is a 3-phase transformer. Let's see what that would look like on a real transformer. So this would be the tap locations. This one has quite a few more. It has 1, 2, 3, 4, 5, 6, 7 taps. 7 tap locations. So that'd be for 7 different voltages, one of which being the nominal system voltage, 3 being higher than normal, and 3 being lower than normal. Here's another one. This one is showing 1, 2, 3, 4, 5 different taps, and it says percent of rated voltage, and then the location for each, and you can see that's where all of the taps are located. They're showing you along the windings. And so again, you could see it like this. So you choose the correct one. You might have to file off some of the resin coating on this little loop here to ensure you got a good connection, and you move the jumper wire down. Finally, we've got the same application on higher voltage transformers, and this is a single phase can type transformer. It's liquid filled and it's pole mounted. And this one, I've got a picture of a nameplate of another same type of transformer, just different color, and it has taps inside. It says 4.5%, 9%, 13.5%. And this one's set up in a little bit different manner in that the taps are located inside, but they're accessed through a rotating dial. And they're accessed that way because the transformer is normally filled all the way up with liquid, dielectric liquid. And so you wouldn't really want people putting their hands in there and tools trying to disconnect and reconnect a jumper wire. So this one is with a rotating dial that connects the taps depending on what you require. So I hope you enjoyed this presentation. We've got another couple coming up relating to transformer applications in the electrical field.